There is a version of this story that would be easy to tell wrong, so it's worth being precise from the very first sentence about what has and hasn't actually been found beneath Antarctica. Because the real discovery is stranger and more consequential than a simple headline can capture. Nobody found a brand new, previously unknown ocean sitting inside the rock beneath the continent, in the sense of some vast subterranean sea, like what researchers have found, through decades of accumulating evidence, is that Antarctica sits atop and is surrounded by an interconnected system of liquid water, some of it locked beneath kilometers of ice in the form of lakes and rivers, some of it flowing beneath floating ice shelves as an extension of the ocean itself, and some of it existing as saturated groundwater within sediment layers under the ice sheet, and all of which together form something that behaves, in practical hydrological terms, like a hidden ocean system, one that scientists have only recently developed the tools to properly detect and map. The distinction between this reality and a more sensational, fictional-sounding hidden ocean matters, because the actual science is genuinely remarkable on its own terms and doesn't need exaggeration to be worth understanding. To appreciate why this matters, it helps to start with what Antarctica actually is, physically, beneath its ice. The continent is not simply rock covered by ice in a straightforward layered sense. Large sections of West Antarctica sit on bedrock that lies below current sea level, in some places by more than 2 kilometers, meaning that if the ice sheet covering that region were removed entirely, much of what remained would be an archipelago of islands surrounded by ocean rather than a single continuous landmass. This detail matters enormously for understanding water beneath the ice, because it means the ice sheet in these regions is not simply sitting on dry land the way a glacier might sit in a mountain valley. It is sitting on a seabed, held in place partly by its own mass and partly by the buoyancy relationship between ice and the ocean water that would otherwise occupy that basin if the ice weren't there. Understanding this configuration is essential context for grasping why water beneath the Antarctic ice sheet behaves less like isolated puddles and more like an extension of the surrounding ocean in certain critical regions, particularly where ice shelves meet the sea. Ice shelves themselves are the most direct and least ambiguous example of ocean water existing beneath Antarctic ice, and they've been documented and studied for far longer than the more mysterious subglacial lake systems. An ice shelf forms where a glacier flows off the continent and out over the ocean, and rather than breaking apart immediately, the ice continues floating on the water's surface, sometimes extending hundreds of kilometers from the actual coastline before finally breaking apart into icebergs at its outer edge. Beneath these floating shelves lies genuine ocean water, often several hundred meters deep, connected directly to the broader southern ocean. And this water is neither hidden nor mysterious in the sense of being undiscovered, since researchers have drilled through ice shelves to sample this water directly for decades. What has changed more recently is the level of detail with which scientists can observe how this ocean water interacts with the ice above it, and those observations have revealed processes considerably more dynamic and consequential than earlier, simpler models assumed. Recent surveys using autonomous underwater vehicles, specialized robotic drones capable of swimming directly beneath ice shelves to map their underside and measure water temperature, salinity, and current patterns, have revealed that warm ocean water doesn't simply sit passively beneath these shelves. In several key locations, particularly beneath ice shelves in West Antarctica, like the one associated with Thwaites Glacier, researchers have documented warmer, saltier water actively intruding beneath the ice from deeper ocean layers, carving channels and cavities into the ice from below in patterns that surface observation alone would never reveal. In some surveyed locations, researchers found that the base of the ice shelf had been eroded into terraced, staircase-like formations, evidence of complex, layered melting driven by how differently dense water masses interact and move beneath the ice, a process considerably more intricate than the uniform, gradual melting that earlier and simpler climate models had assumed. This matters because ice shelves act as a kind of structural brace, holding back the much larger mass of grounded ice sheet behind them, and if ocean water actively undermining these shelves accelerates their thinning and eventual collapse, the glaciers behind them can speed up dramatically, since removing that braking effect allows ice to flow toward the ocean far more quickly than when the shelf was intact and structurally sound. Moving inland, away from the ice shelves and toward the interior of the continent, water beneath the ice sheet takes on a different but equally important character, existing not as a direct extension of the ocean, but as fresh water, trapped and generated beneath the ice through a combination of geothermal heat and pressure, the same basic mechanism responsible for subglacial lakes like Lake Vostok. What more recent research has revealed, though, is that the subglacial water doesn't sit still in isolated lake basins the way early radar surveys initially suggested. satellite altimetry data, which measures extremely subtle changes in the height of the ice surface using instruments in orbit sensitive enough to detect elevation changes of just a few centimeters, has shown that the surface of the ice sheet in certain locations rises and falls in patterns that only make sense if large volumes of water are moving beneath the ice, filling and draining subglacial lakes over periods of months, sometimes flowing considerable distances through channels connecting one lake to another, before eventually, in some documented cases, reaching the ocean at the ice sheet's edge. This finding effectively connects what researchers used to think of as separate, sealed lake systems into a broader, dynamic plumbing network running beneath the entire ice sheet, one that ultimately drains toward and interacts with the surrounding ocean, rather than remaining permanently isolated. Perhaps the most genuinely surprising recent addition to this picture comes from research into groundwater existing within sediment layers, beneath the ice sheet itself, a discovery that adds an entirely new dimension to how much liquid water exists in the system. Researchers using electromagnetic surveying techniques, adapted from methods originally developed for oil and mineral exploration, have found evidence of extensive saline groundwater, saturating sediment layers hundreds of meters beneath parts of the ice sheet, in some surveyed locations extending kilometers deep into the sediment below the ice bedrock interface. This groundwater appears to hold a volume of water potentially comparable to, or in some estimates exceeding, the total volume held in all of Antarctica's known surface subglacial lakes combined, a genuinely startling possibility given how much research attention the surface lake network had already received, before this deeper groundwater layer was properly characterized. The existence of this groundwater matters for reasons beyond simple curiosity about total water volume, because groundwater saturating sediment can influence how easily ice slides over the sediment layer beneath it, potentially serving as another lubricating mechanism, similar in function to surface subglacial lakes that affects how quickly ice moves toward the coast, adding yet another variable that climate and ice sheet models need to account for in order to accurately predict future ice loss. The biological dimension of this hidden water system deserves attention here as well, because water beneath Antarctic ice isn't simply an inert hydrological feature, it's an active habitat, and understanding what lives within it connects directly to understanding how the whole system behaves. Research into subglacial lakes like Lake Whillans, drilled using contamination-controlled hot water drilling techniques, found active microbial communities surviving through chemosynthesis, deriving energy from chemical reactions in rock and sediment, rather than from sunlight, since no light has reached these environments in extremely long time frames. What's particularly relevant to the ocean connection story is evidence suggesting some of these microbial communities and their nutrients get transported through the subglacial plumbing system, all the way to the ocean at the ice sheet's edge, meaning subglacial biological activity may actually be feeding nutrients into coastal Antarctic marine ecosystems, linking what happens in these buried, isolated lakes to the productivity of visible ocean. Ecosystems along the coast in a way researchers hadn't fully appreciated until relatively recently. This creates a genuinely elegant, if still incompletely understood picture of an entire hidden water cycle running beneath the ice sheet, starting with geothermal melting and microbial activity deep in the continental interior, moving through a network of lakes and rivers, and eventually emptying into the Southern Ocean, carrying nutrients, sediment, and fresh water that influence marine ecosystems and ocean circulation patterns near the Antarctic coast. Ocean circulation itself provides another compelling reason this hidden water system matters far beyond Antarctica's immediate vicinity. Cold, dense water forming near Antarctica, partly influenced by the amount and salinity of fresh water entering the ocean from beneath ice shelves and from subglacial discharge, plays a critical role in driving global ocean circulation patterns, sometimes described collectively as the global conveyor belt, which distributes heat, oxygen, and nutrients throughout the world's oceans, over timescales ranging from years to centuries. Changes in the volume, timing, or salinity of fresh water entering the Southern Ocean from Antarctica's hidden subglacial water system, whether through more frequent or larger subglacial lake drainage events, more active groundwater discharge, or increased ice shelf melting from ocean water, intrusion, could influence the strength and stability of these global circulation patterns in ways that researchers are still working to model accurately. This is part of why understanding what's happening beneath the ice sheet has implications reaching considerably further than Antarctica itself, touching on questions about global ocean health, fisheries, and even weather patterns in distant parts of the world that depend, indirectly, on the stability of ocean circulation systems, partly influenced by processes happening beneath Antarctic ice that remained essentially unmapped until very recently. Technological advances explain much of why this picture has come into focus so recently rather than decades earlier, and understanding these tools helps clarify why the phrase discovered applies here even though water beneath Antarctic ice has been suspected in some form since the 1970s. Satellite missions like ICESat and its successor ICESat-2 using laser altimetry capable of measuring ice surface elevation with extraordinary precision from orbit, have allowed researchers to detect the subtle rise and fall patterns associated with subglacial lakes filling and draining, essentially letting scientists map an invisible plumbing system from space by watching how its activity deforms the ice surface above it. Autonomous underwater vehicles capable of navigating beneath ice shelves without direct human piloting have allowed researchers to map cavity shapes and water properties in locations too dangerous or logistically difficult for crewed submersibles or surface ships to reach safely. Electromagnetic and seismic surveying techniques, adapted from resource exploration industries, have allowed researchers to detect groundwater and sediment saturation patterns hundreds of meters beneath the ice without needing to drill at every single survey location, dramatically expanding the geographic coverage possible within realistic research budgets and timeframes. Combined, these tools have transformed Antarctic subglacial and sub-ice shelf water research from a field limited mostly to isolated point measurements at a handful of intensively studied locations into something closer to a genuine, if still incomplete, continental scale mapping effort, revealing a system considerably larger, more interconnected, and more dynamic than earlier point-based research alone could have shown. None of this diminishes how significant the underlying discoveries actually are. And there's a real argument that treating this water system as effectively a hidden ocean in a functional, rather than strictly literal sense, is a reasonable way to communicate its scale and importance to people unfamiliar with the underlying science. This is a body of liquid water distributed across lakes, rivers, saturated sediment, and ice shelf cavities covering a substantial fraction of a continent nearly twice the size of Australia, hidden beneath an ice sheet that gives no visible surface indication of any of this activity, sustaining active microbial ecosystems that have existed in isolation for potentially millions of years in some locations, and connected functionally to the surrounding Southern Ocean, and, through that connection, to global ocean circulation, patterns that affect climate and marine ecosystems worldwide. Describing this as a discovery is entirely fair, even though it emerged gradually across decades of accumulating radar surveys, satellite observations, drilling projects, and modeling work rather than through any single dramatic announcement, because the cumulative picture that has emerged only over the last decade or so, particularly regarding how interconnected and dynamic the system is, represents a genuinely new understanding compared to what scientists believed even 20 years ago, when subglacial lakes were still generally thought of as isolated, static features rather than active nodes within a continent-spanning hydrological network linked directly to the ocean. What remains uncertain, and what continues to drive active research investment into this area, is exactly how the system will respond as the surrounding climate continues warming. And this uncertainty is precisely why scientists studying it describe their findings with a mixture of fascination and genuine concern rather than pure celebration. If warming ocean water continues intruding more aggressively beneath ice shelves, accelerating basal melting and destabilizing these floating structures, the glaciers behind them could lose their main structural brace faster than current models predict. An outcome that would directly affect global sea level rise projections that hundreds of millions of people living in coastal regions worldwide depend on for planning and infrastructure decisions. If subglacial lake drainage events become more frequent or larger as basal, melting increases due to warming-induced changes in ice sheet dynamics. The lubricating effect on ice flow could further accelerate glacial movement toward the coast, compounding the ice shelf destabilization problem rather than acting independently of it. And if increased freshwater input from this expanding subglacial and sub-ice shelf water system meaningfully alters the salinity and temperature of water, feeding into global ocean circulation patterns, the downstream effects could reach far beyond Antarctica, into ocean and climate systems that most people, understandably, never think of as connected to a hidden hydrological network beneath a distant ice-covered continent they will likely never visit. The story of Antarctica's hidden ocean, then, isn't really a story about scientists stumbling upon some previously entirely unknown, self-contained body of water sealed away like a secret the planet had been keeping. It's a story about how a picture assembled gradually, through radar surveys beginning in the 1970s, drilling projects spanning decades, satellite missions launched within the last 15 years, and robotic exploration technology still actively being refined today, has revealed that Antarctica's ice sheet sits atop and alongside a genuinely vast, interconnected, and biologically active water system, one considerably larger and more dynamic than researchers assumed even a generation ago, with direct consequences for global sea level, ocean circulation, and marine ecosystems that extend far beyond the continent's icy, deceptively still-looking surface. That gap between what Antarctica appears to be from above, a static white expanse, and what it actually is underneath, an active, flowing populated hydrological system extending from deep interior lakes all the way out to the open Southern Ocean, is what makes this one of the more genuinely significant discoveries in recent Earth science, deserving of careful, accurate description rather than exaggeration, because the accurate version of this story is already remarkable enough on its own.